Let me just check. We're good? Yep. We have a question.
So say you go like 1, 1, 0.
What's that?
So you go like 1, you're trying to get the number of sine bases, right?
Right.
So say you go 1, 1, 0. Does 0 count as positive or negative? Is that a sine base?
It has to be strictly positive. So yes.
Negative.
So 0 counts as negative.
So if you're like -1, -1, 0, that's not a sine change?
It will always be a leading 1. Right? The Ruth array, right?
Well, how about 1, -1, 0 then?
So if you've got this, so 1, -1, 0
in your first column.
In your first column, and the question is whether you have 2 or 4 poles in the.
Do you have 2 sign changes or 1 sign change?
Or 1 sign change. I think that counts as 1 sign change.
So 0 is negative.
0 is negative. Okay. I think they have to be strictly positive.
I need to change my answer then.
But you got one for the for Ruth?
I have like something 0 from one of the Ruth problems.
All right. Check in the book because it's a little more clear, but I'm pretty sure that 0, so you're going to have in your Ruth array, you're going to have something, it's going to be 1, I don't know, 3, and you said you had -1, 0, something like that.
I read that as well.
Right. But the question is whether this is another sign change. I would say that you have, based on this, you have 2 poles in the right half plane.
1, 2. Okay.
Right, so you get 1 sign change for one, next sign change gives you the other. All right. So I heard some slight rumors that there were a few of you that were confused about stuff. So the way to end that confusion, of course, is to ask me questions. All right, and I will be happy to try to explain it to you differently. All right. So if, however, you are not confused, then I will keep on going. So let me know. All right. So is there anything you guys are confused about? Nothing. All right. Somebody give me a thrill one of these days. Ask me a question. All right. We just to pick up where we. Okay. First of all, it's the important announcement here. Well, that was interesting. All right. So the important announcement is that the midterm, after much thought and consideration and being gentle to the guys who are in 118 as well, we're moving the midterm to the 14th of February. It's going to be a little Valentine's Day present there. And it's going to be in class. The practice midterm is posted. So if you actually follow the link, that actually works now. What you'll see is most of it is about, it's going to be about RootLocus, which we actually haven't gotten into yet. So it will cover not only this homework that just went out today, it will also cover the next homework that's going to go out on Tuesday the 5th. So I'll hand the next one out. The one thing is that in order, what we'll do is we'll make the homework due instead of the usual Thursday, we'll make it due Wednesday a day earlier, and that'll be when I do the review session. And I'll also post the solution set for it as well at the same time. So that way I'll be done with the homework, and doing the homework will be, in essence, a very good way to review the stuff on the midterm. All right, so as the day approaches, so we're going to do the review for it. It's going to be on the 13th of February, 2008, and I'll figure out, it'll probably be somewhere around the 6 p.m. time frame, and we'll figure out where as soon as they give me a room. We're also not going to do the midterm in this room. We're going to do the midterm in a different room, and they're trying to get me a nice big giant cavernous room so we can spread out. And hopefully they'll get me that. So it'll be somewhere. I don't know quite where it'll be. And we'll do full class time. I hate to burn a whole class on it, but that's the way these things go. Okay. We were at the very end of last time, going over PID control, and sort of, the joke is, as I said, there's PID control and there's PhD control, and in this class you're not going to get through the sort of PhD level, so we're going to, in the end, what you implement will most likely be a PID controller, which has this funky form, that K of S is a proportional gain, a derivative gain times a derivative function, right, and an integral gain with an integrator on it. So the 1 over S is an integrator, the S is is derivative. All right. So each of these has a physical sense on what it does. All right. So the proportional gain looks a lot like springs trying to bring your mass back to center. All right. So the bigger you make the proportional gain, the stiffer this gets, the higher the natural frequency goes. All right. And the stiffer the whole system goes, the harder the ride to a certain extent. All right. Likewise, if I take a look at the KD term, this is you're going to get a force that's proportional to the rate of change of your output. And the rate of change, when you have a force that looks like a rate of change, it looks like a dash pot. And it's actually sucking energy out of your system, assuming that there's that minus sign. All right. If it's plus sign, you're adding energy, you're feeding energy into the system, which is generally a bad idea. Certain systems like that, but in general, that would be bad. They tend to blow up that way. And so that has the physical equivalent of essentially putting friction along the way. All right, so that it slows you down as you go. It removes energy out of the system. Okay, and what we did was showed that for a little simple satellite model, 1 over ms squared, all right, that with just Kp and Kd, I can actually move those roots anywhere in the S-plane that I want. So Kp gives me the stiffness, all right, so it gets me out farther on the natural frequency. I just basically realized I didn't have the remote pointer on. Okay, so Kp moves me farther out. Oh. Whoops, that didn't work. I thought I just changed it. Oh, I got the hand instead. I missed. There we go. Much better. Much more engineering-like. Okay. So Kp will move me out on rays of increasing natural frequency. All right? And Kd will sort of fold me over and give me increased damping. So Kp gives me how far, increasing stiffness, increasing natural frequency, but no damping. All right, the Kp actually doesn't give me any damping. In this case, where there's no damping, this is going to it's going to sort of push me out, all right, away from the origin, but it's actually going to push me in the origin away pretty much along the j-omega axis, which means this thing's just going to oscillate at higher and higher frequency, all right, if there's nothing to take energy out, which is pretty typical of the satellite. All right, and the Kd term, the derivative term, is going to bring me back in and sort of fold me down along the lines of constant zeta. All right, so I'm gonna bring that down. One of the things I did here, which was sort of kind of interesting, was we showed that x, in this case for the satellite, is transfer function of x to f of s, transfer function x to d of s. So in this case, the f is what I'm controlling versus with my feedback. Right? I'm saying I'm going to make f some function of x. Right? And so if I write the error to my command, I get this shape, which looks like a type 2 system. And then I have a finite error to a parabolic input, but 0 error to a ramp and 0 error to a step. Whereas, however, if that comes in through the disturbance, right? If it's the disturbance that comes through, I'm actually got an error that is 1 over that, which actually has a steady state error to a single unit step in disturbance. All right? So this is something just to sort of be aware of. This is why I don't like the terminology of what type a system is because you have to be careful about what the input and what the output is. So this system is type 2 to tracking a command input. All right? But it's actually a type 0 when tracking it, when trying to reject a disturbance. Right? And so, if I said, well, look, I want to make sure that whatever disturbance comes in, right, I want an error less than 0.1. Okay, this is I want an error. I want it to attenuate disturbances by a factor of 10. Right, that pushes me to a Kp of greater than 10. All right, so that's what's telling me. Now, one thing I wanted to sort of point out here, when we did the sort of the second order response, right, and I have my envelope. So this envelope looks like an e to the minus sigma t, right, and then inside I have a cosine omega dt plus some phase offset. Okay. This is omega d. If I put this on the real and imaginary, right, I'm going to have my complex conjugate pair. That is omega d, and that is sigma. This is omega n, and this angle is arcsine of zeta. Now, the damped frequency, what it actually oscillates at, is omega d. Why are we so concerned then with omega n? What is omega n? It's a natural frequency, right? So omega d is the damped frequency. Omega n is the natural frequency. Do you guys know the difference? What's that? Right. Did everyone hear that? So if I ping the system, right, and I just whack it, right, I come up with my calibrated sledgehammer and I knock the snot out of the system, right, and I let it ring, right, it's going to oscillate down at omega d, and it'll damp out. Okay? Now, if, however, if I put in a shaker, all right, and I start shaking it at omega d, it'll still damp out. Okay? Whereas, if I actually drive it at omega n, all right, I'm actually going to drive it at its natural frequency. And at its natural frequency, this is where it's going to resonate at. All right? Which means that if I look on a Bodhi plot, for instance, right, I'm going to find something that looks like that. And that peak is going to occur at omega n, all right, where this is going to be the magnitude versus the frequency. All right? So all of a sudden, there's going to be a frequency at which the system actually provides amplification. Right? And that height, by the way, for the double E's is related to Q. All right? So that's the Q of your frequency. So when you make an oscillator, you're trying to make that Q very, very high. All right? So that it picks up and it shakes at that one specific frequency. All right? So I just wanted to make sure that you guys sort of... All right, the reason we use this, by the way, is because we can write the transfer function as s squared plus 2 zeta omega n s plus omega n squared. It's a very convenient form to carry around, and of course, that term then is very obvious. Whereas the omega d is slightly more complicated to pick out, because to write it as omega d, I've got s plus sigma squared plus, what, omega d squared? Is that right? So I've got to write it like this, which is a slightly more complicated form. All right, so there's sort of historical reasons we carry that around. Okay. Yeah.
Is omega d kind of like the 3 dB point of a filter state?
No. No. So omega d is where it will, the frequency you will actually see if you pull the thing away and let it go. Okay. All right. So if you give it a ping or an initial condition response, and you watch it shake, and you measure the frequency that you see in the system, you'll see omega d. Okay, and it'll shake back down, but it'll beat at omega d. Whereas if you want to see the maximum amplitude you can get on the system, and sort of the 3 dB point would be for a low pass, right, or a high pass. There is no resonance there, right? So the resonance you'd see is if it, this would be a typical second order response, all right? And then, well, it's not 3 dB anymore, right? You can get this little peak up there, which if you're designing, Chebyshev or other kinds of filters, you can actually tweak that peak to make it go up and do things like it, you get things that do like that, so you get things, neither here nor there. But no, so it doesn't. So omega n is the resonant frequency. If you're going to shake the system, where is it going to want to shake at? Where do things start falling apart, essentially? So if you take a car, for instance, all right, and you and your buddies see someone's car and you want to mess with them, you go and you push the car and it comes back, very damped response, little oscillation. The oscillation that it shakes at is omega d. However, if you actually really want to get it moving, you get two guys on either side and you start pushing it back and forth, the frequency that you want to drive it at in order to maximize the amplitude that the body is shaking is omega n. right? And they're close, but they're not exactly the same thing, right? So that's the thing. Okay.
Is there any case where those two frequencies are the same?
Yeah. There's actually, I mean, you can, because omega d is equal to, what is it, square root of 1 minus zeta squared, omega n, right? So if there's no damping, then yeah, they're exactly the same, right? So omega n is where it would oscillate if there were no damping, essentially. Okay, so it's the undamped frequency. Well, if you're feeding energy in, you're driving it at a specific frequency, then it's going at that. It's going to go at that frequency. Okay, so let's see. Here were some. These are examples from something that we don't need. Okay, so. Let's review the bidding here. All right, we've done analysis, and our analysis tools are actually pretty good at this point. All right, we've gone fairly far down this road, and let's see. Ignore that. We can now do. We can go from equations of motion to Laplace transform. To closed loop, to open loop, and closed loop transfer functions. All right. We can do the response to a variety of inputs. I can actually anticipate what the response is going to look like simply by factoring the denominator of the characteristic equation. Right. Factoring the denominator of the transfer function gives me what that looks like. And I say, hey, this is pretty cool. I can, given, I now know sort of, I also have a vague understanding of my specs to operating on the S-plane. All right, so basically, given some time domain, I can now map this to the frequency, to the complex plane, and get regions of interest, and start telling you sort of what the response looks like. And all of this works particularly well. So, given a G of S and a K of S, I can do, a reasonable amount of analysis here. All right. It gets a little messy once we're beyond second order. All right, but I can still do it. So right now, the chain is going to go something like, physics gets us to equations of motion, which through the Laplace gets us to a transfer function, which then we can take through some basic analysis, and then we want to go into design. All right. So far, we've glossed over the physics and assumed you all knew it. We've done a little bit of equations of motion. We've spent a lot of time on doing Laplace transfer function, and we've pretty much finished up doing all our analysis. All right. So now we're sort of drifting over into design. All right. What we've done is the first basic part of design is, well, I got to know what it is I want. So how do I translate what I want to things that I can actually quantify? All right. And what we can do sort of now is if I give you some form of K of S and some specs, basically what you do is you wind up matching coefficients, and and this works pretty well for things that look approximately second order. All right. So what we need is a better tool. All right, better tool for design, and that's going to be in Chapter 5. And the tool that we're going to use is the RootLocus. Okay, we're going to creep into this a little slowly. All right, so it's going to be, not all at once, but it's definitely going to be, it's going to be kind of interesting. Okay, so let's start with a real simple system. Okay, we're going to have G of S is equal to 1 over S plus 2. All right, And I'm going to put this in my standard. Here's my reference input. I'm going to put it through a compensator that looks like just a straight gain K, my plant, and unity feedback, and here's my output that I'm interested in. All right, so K of S in this case is equal to just my gain K. And I've got that Y over R, right, my output to my tracking command, is going to be GK over 1 plus GK, which in this case is just going to be K over S plus 2 over 1 plus K over S plus 2. And that's just going to equal to K over S plus 2 plus K. All right, so far, so good. A little basic algebra. We all know how to do this. Out of curiosity, what's my error over my reference going to be? Anybody?
1 over 1.
Which is equal to in this case?
1 over 1 plus K over S plus 2.
Right. All right. So just to note that my tracking error in steady state to my input is different than my error input. My error is in steady state. Okay. So, because in steady state this is going to be K over S plus 2, or sorry, K over K plus 2, right? Which as K gets big looks suspiciously like 1, right? Whereas this is going to be 2 over 2 plus K, which as K gets big is hopefully going to go to 0. Right, so that hopefully should make sense to you. Okay. So my characteristic equation is simply the denominator. Realize that the denominator is always the same. And even if I had a disturbance input that came in here, right, the denominator would still be the same. All right. So the denominator is always the same, and it's S plus 2 plus K. Okay. So I've got that so far. Now, if I take my roots of my denominator and I want to plot them as a function of my gain K. So here's the real. Here's the j omega axis. So when K is 0, where's the root start? -2, right? So I'm going to start with my root at -2. Okay? When K is 1, where has this gone? -3, right? So this is the point where K equals 1. What about when K equals 2? -4, right? What about when K equals 100? Where's it going, right? The whole point is that this root is taking off in this direction, right? It's taking off in that direction as a function of K. All right? So I can pick, any point here, and I can say, I can actually determine that if this is the -5, then K equals 3. All right? So the part about this to understand, all right, is that it doesn't matter which input, all right? For any input, I'm going to have, make it GK. This denominator is going to be the same for any input, whether it's noise, reference, error, disturbance, it doesn't matter. Okay? That denominator is always going to be the same. Okay? And what that means is that the poles of, so what I'm looking at is I'm looking for the poles of 1 plus GK equals 0. Right? The poles of 1 plus GK equals 0 are going to tell me what the basic mixing blocks of the time response are. Right? So basically, in this case, I know that I've got a response that looks like an e to the minus 2 plus k t. Right? The larger I make t, the faster this thing decays to 0. Right? So this is a very trivial one. Right? But so looking at this carefully, all right, that means that I can rewrite this as g of s, k of s equals to minus 1. Right? All I did was pull 1 over there. At first you may think, hey, that's not really a big deal. Okay? This is actually a huge deal, and I'll show you why. All right? Let's go back to a little bit for a second, and I say, all right, just take a look at the frequency response that we did. All right, so I have my plant. There's my plant today. All right, and I stuck in an A cosine omega t, and what I got out was what? What was that? Right. So I got out a AM cosine. We call it plus p, but okay. So we got out a shifted and scaled version of the same cosine wave. Now, if you remember this, so essentially, I had the m is equal to I had g of s, in this case, was equal to some numerator of s, denominator of s, evaluated at s equaled j omega. Right? And that the magnitude was going to equal to the magnitude of g of j omega, and the phase was the angle of g of j omega. So what we were doing was we were taking, on our complex plane, right, I was taking a point on the j omega axis, right, and I was sliding up and down and evaluating the magnitude and the phase of this function. Okay? Now, the question I have is, so for what value of s is, so looking at this very carefully, okay, I want to know for what value of s is g of s, k of s equal to minus 1. All right. So let's take a look at this rather carefully. So now, instead of looking just along the j omega axis, I'm going to look everywhere in this plane. All right. In other words, now I'm no longer restricted to just s equals j omega. I'm now looking at points where s is equal to some sigma plus or minus j omega. Right? And I'm looking for this, and somewhere when I substitute that s into gk, I'm going to get minus 1. All right? What's it mean that it's minus 1? What is minus 1? Well, that's j squared. Well, there is that. That is tautology. If I've got g of s, let's assume for now that k is just a constant, right? So if I've got g of s evaluated at s equals sigma, we'll do plus or minus j omega, what am I going to get out of this? What did I get before when I did this, right? I just got a complex number, right? It's just a complex number, right? So in this case, this is going to equal to some complex number that has a magnitude, and it has a phase, right? I don't necessarily know what it is, but it has a magnitude and a phase. And if k is just a constant, all right, then when I say k m e to the j c is equal to minus 1, all right, what does that tell me? Well, it doesn't tell me anything about stability, all right? But you did catch a thing. It means that the magnitude, right? The magnitude of KME J phi is equal to what? 1. And the phase of KME to the J phi is equal to plus or minus 180, right? Or pi, if you're working in radians. Okay. So this is a big deal. Okay. Now, the magnitude is only a function of, the phase is only a function of the angle, and the magnitude is only a function of the scalar outside. Okay. So basically, what this says is that if I'm looking for places in which I can find a phase of plus or minus 180, and once I find anything that has a phase of 180, I can figure out what k I need to get me a magnitude of 1. Right? Let me do that slowly again, okay? Let's say I have some function, all right? Let's just do that. I've got g of s evaluated at s equals sigma plus or minus j omega, all right? And what I get out of that is some magnitude and some phase, okay? So if I can find the s's that make this whole thing have a phase of 180, so I'm looking for the angle of, essentially, the angle of MEJ phi is simply equal to phi, all right? And if I can find where that equals plus or minus 180 degrees, all right? So I'm going to search the S-plane. I'm going to search until I find areas. Here's a spot. I found a spot where the whole thing has a phase of 180. All right? Now, in order to find the magnitude that puts me at minus 1, all I've got to do is say k is 1 over, essentially, m. Right? Pick k equals 1 over m, and this now is minus 1. Right? That point, that s equals j omega point, now has, if I punch it through kg, all right, evaluated at this point, it's negative 1. I feel I've lost you all, or I'm boring the hell out of you. I'm not sure which. Someone, say something. What's that?
Pretty much my instinct says that this is a completely unstable system.
No. Okay. So remember that we are looking for. No, it's not. And okay. So all we're looking for is the roots of 1 plus gk equals minus 1. All right. So.
If on the output you have negative 1, you feed that back, and you're essentially adding to your input.
Yeah, but it's negative feedback.
Okay, yeah, but on the output you have negative 1. So it's negative.
No. Okay, careful here. All right. We're looking for the roots of the closed loop system. Okay, the roots of the closed loop system tell us how the system is going to respond. All right. What we're doing to find the roots of the closed loop system is we're saying look for where the open loop system, gk, is equal to negative 1. If I can find where gk is equal to negative 1, then I'm at a place where I'm at the roots of 1 plus gk. Right? And remember that the roots of the denominator tell me how I'm going to mix together my final response. Right? So by looking at where the roots move, right, where the roots of the open loop system move such that I'm looking for where the gk equals minus 1 means where is the denominator or the characteristic equation 0, where are the roots of the characteristic equation. By moving those roots around, all right, that allows me to take a look at where what building blocks I have for the output. Yeah, Shane.
So in this example, when you say move the roots around, that means change K?
Yeah. So in this case, right, in this particular case, all I've got to tune it is K. All right? And with K, what we said was, hey, I'm fairly limited in what I can do. All right? All I can do is move it along that line. All right? And if I'm willing to actually make K negative, I go to positive feedback. I go to a destabilizing one. I can actually move it in this direction. All right? We'll get to that a little later. I don't want to confuse you, but you can usually do both sides of it. But nonetheless, here I'm fairly constrained. All right? But the idea is, if I can figure out how the roots move, okay, then I can actually figure out, hey, the roots aren't going where I want. Let me put something else in there that moves them where I do want. All right? And this is how we figure out how to design compensators. All right? Now, what I'm trying to get to right now is just figuring out what we're doing, just how to evaluate the plant as a complex number. It has magnitude, it has phase. So I'm going to search the S-plane, right, looking for spaces where essentially the phase of G of S is plus or minus 180. Right? And this is why it's called, by the way, the 180-degree root locus. And this GK equals -1. All right? This is referred to as the Evans form for Walter Evans, who came up with this in the 1950s, I think. And truly, it's kind of a funky way to look at it. And we'll do a little bit more, and I'm hoping that I can get it to the point where you're going to look at this and you're going to say, hey, it's going to be a little confusing at first. We're going to take it slow. And, when it's, hopefully at some point, the penny will drop and you guys will be, oh, okay, I get it. All right. If it wasn't easy, it wouldn't have lasted. So once we sort of get behind sort of why it works, you'll see that how it works is actually pretty damn simple. And what it allows you to do, it's an extremely powerful technique. In essence, what it allows you to do is factor high-order complex equations in pretty much as fast as you can draw. All right? And you can do it to pretty good accuracy and, in a couple of seconds. Sketch, 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 and now you understand what the system's going to do. All right? And you can tailor your response to where you want. And when you want to pick the actual response, you can pick it off. All right? So anywhere on G of S is equal to, the phase of G of S is equal to plus or minus 180, all right, is going to be on the root locus. Right? That means that those points are all those points that line up everywhere that S such that the angle of G of S evaluated at that S is 180, right? Everywhere there is somewhere on the roots of the closed loop equation. Okay? You're constrained, right? You can't get off of those roots, right? But by varying your parameter, in this case K, right, I can move along it. It tells me where do I necessarily want to choose, right? If you think about it, if I take so I'll just do something I'm just going to sketch it out right now. You guys are going to think I'm a little nuts, but I'll do it. All right, so here is a system that has a pole here, a pole here. All right, and hopefully by the end of class we'll know how to do this. Basically, the root locus in here is going to do, that one's going to come towards here, this one's going to come towards here, they're going to meet in the middle, and they're going to split, and they're going to go up at 180 degrees from each other, and they're going to go out to infinity that way. All right. All of a sudden I said, hey, given this system, which looks, by the way, like a 1 over S plus A, all right, I can tell you what, if I add K here and put this in a feedback loop, I can tell you where it goes as a function of K. Right? Now, if I put on top of this and I say, okay, well, I've got my specs for designing the system, and the specs were I need a rise time of so much, and that's going to do something like that. Okay? And then I need a damping ratio, an overshoot spec, such that I have a damping ratio that's something like this. I say, hey, I have an answer. I need to find the K that puts me right in that little corner that meets all my specs. Right? Once I know that this is the spot I want to put them in on the root locus, right? Then finding what the gain is that puts me there is a relatively quick exercise, and we'll get to that in a second. Yeah.
So when you say the two roots are going to move towards each other and split,
Mm-hmm.
how can you
Indeed, we will get to that.
K is just a scalar, right?
K is just a scalar, but 1 over SS plus A, right? So what does the closed loop transfer function look like? Okay?
Oh, so it's S, or sorry, K over S, S plus A.
Right, so it's going to be K over S plus A, right, all over 1 plus K over S plus A, right?
Right.
So this is going to be equal to a S squared plus AS plus K, okay? So where are the roots of that going as K changes?
Oh, I see. Eventually parabola.
Right.
Yeah.
Yeah. You could call it a bifurcation, yeah. All right. There's we'll get to all sort of the cool things that the root loci do. All right. And there's now I've been doing this for a while. All right. So you can basically throw up just about any pattern of poles and zeros, and I'll be able to sketch it out in about as fast as my hand can move. All right. That comes with familiarity. I don't expect you guys to be able to do that just off the top of your heads. All right. But the rule there are a bunch of rules. The rules are pretty simple. And, this is sort of, getting in touch with your inner kindergartner. It's going to be drawing and, sketching things out and with a little bit of calculation. But the whole point is that we can do this really simply. All right? And by doing it simply, we can get an enormous amount of intuition. Because what this is actually telling me, I have a system, all right, SS plus A, all right, that as I start to crank up the feedback gain, I say, hey, the system starts to get faster because this one's going to be the dominant pole, right? Because as it moves slowly off the origin, all right, it's the system's getting faster in its response. And then I get to a point where all of a sudden the system starts to oscillate. It didn't oscillate before. Now it starts oscillating. As I keep cranking it up, as I keep cranking up the gain, that system gets faster and faster and faster. All right? And I can tell you that not because sort of I understand the physics behind it, but just because of this intuition that this gives me. All right? Which is why, by the way, when you're tuning PID controllers, they say, crank it up until it starts to oscillate. All right, well, what are you doing? You're bringing these two together, and then as soon as they split, right, and it starts to oscillate, you say, oh, I've left the realm of where I need to go. Back off a little bit. All right? So these are now the kinds of oscillations you're going to notice. All right? Something that's particularly well damped, and you actually won't notice anything pretty much within about a 30-degree cone of the real axis, all right? Because it effectively doesn't go through any cycles, all right? This is, we're talking about less than a 5% overshoot. It won't rebound. You won't come back. So when you start to oscillate, you're actually getting up sort of past the 45-degree line, and you'll start noticing it start to shake. Right. You'll see ringing. All right. And once you see ringing, you're like, oh, okay, I'm getting in the dangerous zone, and now I'm going to back off a little bit, and now I'm going to sort of adjust the next knob to give me better damping. All right. And as I said, there's all kinds of methods on how to tune PID controllers, some of which work. There's even a company that if you send them your data, they will send you back what they think are the optimal gains, and they guarantee that you can't find any better. So anyway, all right. So the whole point of what we're doing is we're trying to look for basically all of the places where the poles and zeros come from, and we're going to factor out one constant gain or one parameter that we're going to vary. Right? We want to look to see where do they move as a function of that parameter. Okay. In this case, let's just assume that it's a constant gain, and I'm going to search the complex plane for areas where G of S has a phase of 180. All right? So that's what I'm looking for. I'm looking for a phase of 180. And everywhere I find a phase of 180, right, I know that I'm potentially on the root locus. How do I get exactly on that point? Pick K so it's 1 over M, and I'm at that point. All right? But anywhere the phase is 180, I'm potentially on that point. All right? And it's just choosing the right gain to put me on that point. So all I've got to do is find the branches of G of S, right, in the S plane as a function of this S, complex S that's going around, such that the phase is 180. This is how I'm gonna do it. Okay. Now, just to preface this a little bit, we'll get there later. So if I can find a point with GS, let's call it KGS, has a phase of plus or minus 180, all right, then the other way of saying that is that the angle of ME to the JC, which is equal to 180, then K is equal to 1 over M. All right? Now, just to confuse you, so the 180 degree root locus, that means that we're looking for 180 degrees, plus or minus, right? Modulo 360, right? Go around as many times as you like, you're still looking for the angle being 180. Okay? So if I'm doing the 180 root locus, this is K is positive or negative feedback. Okay? That's the normal one we're always looking at. I want you guys to be aware of the fact, and we'll learn it later. It's actually just, once you know how to do one, doing the other is all right. If I look for the 0 degree root locus, this corresponds to K as negative or positive feedback, which under normal circumstances is destabilizing. However, because in this case, instead of it being 1 plus GK, it's now 1 minus GK. So if it's 1 minus GK, then GK is equal to 1, not minus 1. So I'm looking for 0 degrees instead of 180. That's sort of doing it. Okay. So for a more complex compensator, I'm going to have that K of S is going to equal to some K naught, a numerator in S, and a denominator in S, and that Kg of S, I guess let me write this as a K of S, G of S, is going to equal to K naught, N of S, and G of S over D of S and dG of S. All right. So all I'm doing is saying I'm still going to plot the root locus against the constant gain, all right, that I extract out of my compensator. All right. And I'm just going to collapse all of this, all of the dynamics, all the functions of S into my big G of S. All right. So let's do this. All right. So we're going to do our simple example, and let's see if we can find it. And then we're going to hopefully get into this, and you guys will see that it's not. It appears intimidating. It's not that hard. Okay. Okay. So we had our G of S was equal to 1 over S plus 2. Okay. So now I'm going to plot this, and here is, this is at minus 2. All right. So I want to evaluate it first at, I'm just going to probe a whole bunch of places on the S-plane and see if I can find, we already know where it is, but let's see if we can find it. Okay. So let's pick S equals 0. That's a good one. All right. So for S equals 0, I've got that, so G of S evaluated at S equals 0 is equal to 1/2. All right. So that means that the magnitude is 1/2, and the phase is equal to 0 degrees. Right? Everyone sort of with me so far? Okay. Let's take a look at, let's move up this way, and I'm going to pick S equals 2J. All right. So G of S evaluated at S equals 2J, all right, is going to equal to 1 over 2J plus 2. All right. So the magnitude of this, right, is going to be essentially 1 over 2 squared plus 4 squared plus 2 squared plus 2 squared square root. So that's 1 over square root of 8. And the phase angle, all right, is going to be arctangent of 2 over 2. right, which is 45 degrees. Right? So far, so good? Okay. Likewise, if I go here and just S equals j omega, all right, some point here, g of s evaluated s equals j omega is going to 1 over j omega plus 2. So the magnitude is going to be 1 over square root of 4 plus omega squared. And the phase is going to be arctan of omega over 2. Right? Everybody with me so far? Okay. So we've done that. Let's go out in this direction. It's symmetric. So I don't, right? The only thing that happens when I go to negative j omegas is my phase is going to flip sides. Right? That's it. Everything else is going to be the same. Right? So let's go out here to, I don't know, s equals a. Okay? So, well, let's start with 2. All right? And then we'll do another one with just generic. Okay? So g of s evaluated at s equals 2 is 1 over 4. All right? So the magnitude is equal to 1/4, and the angle is 0. Okay? And if I do some, let's call it sigma, all right, out here, I've got g of s evaluated at s equals sigma is 1 over sigma plus 2, which has a magnitude of 1 over sigma plus 2 and a phase of 0. Okay. Let's see. Let's look at this spot out here. Okay, s equals to minus 4. All right. So here I've got g of s evaluated at s equals minus 4 is 1 over minus 2. Right. So this has a magnitude of 1/2 and a phase of 180. Ha! Found the spot. All right. So for this specific spot to be, for the root to be right there, right, I say that the gain has to be equal to 2. Right? K is 1 over m is equal to 2. Okay. Likewise, I can search any spot here. Any spot on here is going to have the same thing, just the gain is going to be different. All of them are going to be negative numbers in the denominator, which means they're all going to have a phase 180. Yeah? So far, everybody with me? Okay. Now, let's do a teensy, let's see, do I want to do one of the complex ones just for giggles? Do I want to sort of come and take a look at that point right there? All right. Let's do a little bit of complex number review here. Okay. Because what you're going to see is this is actually a lot easier than it at first appears. All right, so let's say I have a complex number that looks like, so here's going to be the real axis, and here's the j omega axis. And so I have a complex number that is a plus bj. Right? There's my number. So m, if I turn this into a plus bj is equal to m e to the jc. Right? So this is going to be Cartesian coordinates, polar coordinates. Right? So m, right, is this length. Right? So m is just the square root of a squared plus b squared. And phi is the arctangent of b over a. Right? Hopefully this is not a mystery to any of you. All right? Okay. Now, what if I have a ratio of two complex numbers. Okay? What if I say I have another number, okay, which, let's put it out here. There's going to be C, and here's going to be D. All right, and I want to know what I've got A plus BJ divided by C plus DJ. Right? So this is going to be M e to the j phi, let's call it M1 E1 j phi 1, divided by M2 e to the j phi 2. Okay? So far, with me? Well, this is just equal to M1 over M2 e to the j phi 1 minus phi 2. Right? Anyone not seen this before? Okay. Am I boring you? Or is this okay? I'm telling you, the silence just doesn't work. All right. So, given this, all right, now, what if I multiplied them together? What if instead of having A plus BJ divided by C plus DJ, what if I had A plus BJ times C plus DJ? Right? This is going to equal to M1, M2 e to the j phi1 plus phi2. Right? And if I had a reciprocal number, right, if I just had 1 over C plus DJ, so everyone see where I'm going with this, okay? All right, if I just had 1 over C plus DJ, that's just 1 over, I guess in this case to be consistent, that's M2, e to the minus j phi 2. Right? Because all I did was, well, that's just 1. Right? And if you want, I can do the, I can do that this 1, right, is nothing more. This is going to be 1. Well, 1 is 1 e to the j 0, right, divided by M2 e to the j phi 2, which is just 1 over M2 e to the j 0 minus phi 2, which is e to the minus 1 over M2 e to the minus j phi 2. All right. I know how to multiply. I know how to divide. I know how to take reciprocals. Okay? All of these are relatively straightforward. Okay? Now, let's take a look and let's say, all right, so given this, all right, we say, wait a minute, I can now come up with a procedure, like a brute force search of a way to do this. All right, let's say I have yada yada yada. All right. So let's say, for example, I'm going to take my S-plane. So first step I'm going to do is guess a location. All right. Then from there, I can evaluate G of S, right, at that location. I can make this a little bit faster if I use MATLAB. All right. I can say that the magnitude is the function absolute value, and the phase is phase times 180 over pi, all right, to get me back into degrees. Right? And if phi is equal to plus or minus 180, right, k is equal to 1 over the magnitude, and then guess a new location. All right, and I can do this brute force search, right? I can just sort of run around trying to find places where, I can search the whole S-plane. Clearly that isn't terribly efficient, all right? But there are tricks of how to evaluate this, and we're going to see it right now. Okay. For the first one, let's say g of s is equal to s plus a. Okay. So on the complex plane, that means that I have a 0 at minus a. Okay. Why is it a 0? Because this is in the numerator. Right. Such a beast does not exist in nature, but it's easy enough to do. Okay. So I want to evaluate this at, let's pick a point here at s equals j omega. Right? And I want to evaluate g of j omega. That's going to be j omega plus a, right? Which means that m is the square root of omega squared plus a squared. All right? And phi is arctan of omega over a. Now, this height right here is omega. This distance right here is a. What is that length? Right? That is omega squared plus a squared. This is m. Okay? What is this angle? Arctangent omega over a. All right? Hey, that's pretty cool. All right? So, to evaluate this at any point, let's do, okay, so that's just for sliding on the j omega axis. Okay? What if I slide along, all right, so there's minus a. All right, so this is a. All right, instead of being on the j omega axis, I'm going to slide at some point up here, okay, and I'm going to evaluate this point. So now this is going to be at sigma plus j omega, all right, or it's minus sigma plus j omega, all right. Okay, so they're now looking for g of s evaluated at s equals minus sigma plus j omega, all right, which is equal to minus sigma plus j omega plus a. Okay, so the magnitude is the square root of omega squared plus a minus sigma squared, right? And the phase is the arctangent of omega over a minus sigma, right? Can you guys convince yourself that that's true? All right, so now, but take a look. What's that? That distance is a minus sigma. What's that length? This length is m. All right. What is this angle? That angle is phi. All right.
It's the same as doing it from the origin, right? Yeah.
Well, you've moved the origin to here. All right. But the point is I'm now probing for another spot. Okay. So all of a sudden, I say, hey, wait a minute. This is pretty cool. All right. This is geometry. All right. And I can now start looking around, and I can say, hey, if I need phi to be 180 degrees, all right, that's pretty easy to identify. All right. Phi, to get phi 180 degrees, hey, I know I have to be here. How do I know I have to be here? Well, because that's the only thing that gets me to 180 degrees. All right. I can see here that as I bring this point down, phi goes to 0. As I bring it around to this side, phi goes to 180. If I needed phi 90, I'm right above this. Right? I can look at this angle and immediately figure out where I want to be. All right? Hey, this is getting better. Right? Now, you say, okay, great, but I don't ever see a g of s that looks like this. All right? So let me go. We're going to piece this together slowly but surely. All right. So So now we say, hey, I want a pole here. So now G of S is going to equal to 1 over S plus A. Okay? So, if I, shall we just go for the interim spot, or shall we? Let's just go for it directly. Okay. Here's a spot I'm going to probe. J omega sigma A. All right. So now G of S evaluated at S equals minus sigma plus J omega is going to equal to 1 over J omega plus A minus sigma. All right. So the magnitude is equal to 1 over omega squared plus A minus sigma squared. And the phase is minus the arctangent of omega over A minus sigma. Okay? So, now, this is A minus sigma. That is omega. This length is now what? What's this length correspond to? 1 over m. What does that angle correspond to? Right? Minus phi. 1 over m minus phi. Does this perhaps strike a bell? Of 1 over m and minus phi. Right? Now, right? Again, hey, I can find this. What do I do when I have multiples? Okay, so we've done for a single zero. I can find everywhere the angle and the magnitude. Right? The magnitude is simply the length, and the phase is simply the angle from the horizontal to the ray that points at the probe point that I'm putting in. Okay. For a pole, okay, this is something that's in the denominator of the open loop function. Right? The length is 1 over the magnitude, right? And the angle from the horizontal is negative of the phase.
Does that mean we use RootLocus with zeros?
What's that? Poles? Zeros and poles. So basically, G of S can be a polynomial. Right? G of S can always be a polynomial.
So what I'm saying though is that RootLocus means for.
Yes.
Okay.
And we will right now all I'm showing you to do is how to evaluate magnitude and phase in the complex domain. Okay? So what if I have, here's a real simple one. Okay? Let's go together and let's say that I have a pole here and a zero here. Okay? And now I want to find what the phase and magnitude of these are for different S's. All right? So the way I'm going to do it is pick a spot, anyone. Let's go here. All right? Here's my probe point. Okay? So let's call this L0, Lx. Here's phi x and phi 0. Okay? The magnitude of, say, G of S evaluated at S equals that point, right, is going to equal nothing more than, so the magnitude of it, right, is going to equal to L0 divided by Lx. How many of you did I lose in that step? Shane's asleep, so it's not so struggling to stay awake here. All right. All right. So basically, the length of the zero, right, times the length to the pole. Right. That's just m1 divided by m2. Right. And the phase of G of S evaluated at S equals that probe point is nothing more than phi 0 minus phi x. Cool. Now hopefully you're going to say this is actually not that hard, right? So, okay, that's 2, you say. Great. How about if I get really nasty, right? What happens if I give you, something that looks like, let's do those 3 poles, and let's do 2 zeros in between, all right? And I want to find out, at this point, I want g of s evaluated here, all right? How do I do it? Right. So, find the length. All right. So here's the length of my 3 poles. Here's the length to my 2 zeros. Let's call this L1, L2, L3, L4, and L5. So the magnitude is simply L1, L2 over L3, L4, L5. All right. Phase. Okay. So for this one, all right, I'm going to take that angle, all right? So phi 1, phi 2 minus, I'll just match it here. There's phi 3, there's phi 4, and there's phi 5. Pretty nifty, huh? All right. Now, like, okay, this is pretty neat. And you say, well, that's all well and good, but what happens when I give you that? And I say, evaluate it here. Okay? So, how do we do it? Okay, so let's take a look here. All right, so here's going to be, so this is L1, and this is phi 1. All right, here's L2, and here is phi 2.
Shouldn't phi 1 be on the other side, like be greater than 180 degrees? Not less than 90?
Let's see. Yeah, it should be this one. There we go. Okay, so the way I look at this, right, this is going to be, so let me do it slightly differently, just so it matches what I have as my example. All right, so I'm going to put these 2 here, and I'm going to put my probe point here. All right, so this point here, we said this was minus A plus JB, and this here is minus A minus JB. Okay? And then I've got my point up here, which is at minus sigma plus J omega. All right. So this distance is A minus sigma. This distance here is omega minus B. All right. And there is my angle. Okay. And then I've got this distance. All right. So this distance down here is still this is A minus sigma right there. This distance from the top all the way here is omega plus B. All right. And I now want to evaluate G of S is equal to 1 over S plus A minus J JB and S plus A plus JB. And I want to evaluate this at S equals minus sigma plus J omega. All right, and well, I can do all of that, but the easy way is, again, so call this L1, call that L2, call that phi1, call that phi2, and the magnitude of it is just going to be 1 over L1, L2, because these are both poles. Right? And the phase of it is going to be negative phi1 minus phi2. All right? Coolness. Okay. Now, lest you think all of this was kind of a mysterious and crazy way of doing it, I'm probably one of the last people who was ever taught to do it this particular way, and you guys will be spared this. However, what they used to have were essentially plastic protractors that had, so if you look at the protractor, it had a protractor all the way around, right, 360 degrees, pinned to a little bar that was clear plastic. And so what you would do, since you're only looking for the phase, right, is you would have, oh, I don't know, pole, 0, 2 poles, some complicated system, right? And so what you would do is you would stick this thing, set it up so that it currently was at 0, right? And you would pick a point that you wanted to evaluate. So let's say you wanted to pick, oh, I don't know, this point right here, right? So you would stick this thing up here, and you would hold the protractor part against the page, and you would move the bar until it lined up on the 0. Put your thumb on top of the little dot in the center, that little rivet. Spin the whole thing back up to horizontal again. Pin this back down. Go to the next 0. All right? That just added the phase of the 2 zeros. All right? Then you would rotate down to the first pole. You would stick your finger on the center again, so nothing rotates. Rotate it down to the first pole. Pin the wheel. Go back up to horizontal. Do it for the next, for all the poles, all the zeros, and then look at it and read off the phase. All right? It doesn't take very long to get actually very fast at this. All right? Where you, huh?
You have to solve for the poles and zeros and then draw it really accurately first.
Well, you just draw it to scale. I mean, it doesn't. Yeah, you have to solve for the poles and zeros, and you do have to do that. You have to factor it, and you have to do it reasonably accurate. However, given a set of poles and zeros, with one of these things, you can actually, spin around and get very accurate points very, very fast. All right, and then there was a little log scale on the thing part, so you could actually measure the distances out. And because it was all log scale, you just add them all together, and that would give you your gain. All right, so it's called a spiral. If anyone wants to look it up, there was and they used to do this. All right, before you went and sort of fired up MATLAB, this was the way you did it. You point out one of the problems is you need these points reasonably accurately, and factoring it in the first place can be kind of hard. Although when you didn't have easy access to computers, it was sometimes easy to get it factored, but not easy to redo it multiple times for multiple points. All right. So now let's look at what we do with all this. All right. So again, this is interesting, but it's a little too hard. All right. But this is how you do it. But right now, I want you to sort of gain this geometric intuition of what it is you're looking for. And this just falls out of using complex numbers in their polar form. All right, nothing more complicated than that. All right? And notice, of course, that now I've got a root locus. I can tell you where the roots are going as a function of my gain. And if I know where my roots are going as a function of my gain, and I know where the acceptable regions within my complex plane are, I've got design here. All right? I can actually say, hey, I know exactly what I need to do to make my system hit the specs that I need. Furthermore, if I say, hey, well, let me just sort of get philosophical on you. All right. Let's say I've got a system and it looks like 2 poles on top of there, and it's got let's put a 0 here, and okay. Let's just do that. There's your system. Okay? And when I put feedback into this, what I'm going to get is this is going to go this way. Let's see, what am I going to do here? Yeah, let's make this less complicated. Let's see. Yeah, let's. All right, we'll leave it the way it was. Okay, this pole is going to move this way, and these two are going to do something funky, like they're going to do something like that. Okay, and we'll get to how you sort of draw this, but they'll do this. All right. Now, if my specs happen to be that I need to be here, all right? So I've got a settling time spec, an overshoot spec, and a rise time spec that gives me all of these, all right? And maybe I'll have a steady state error spec that will tell me how big one of the gains has to be, all right? But I've got this, and here's my acceptable region, all right? And I say, hey, guess what? It doesn't matter what gain I put in there, I'm not going to get there. Right? And you say, well, what happens if I do something like this? All right? Or maybe I'll put this this one a little farther out here. Okay? This one's going to come in this way, but it's going to have the effect of bending these branches out like that. All right.
So was that a pole that you added to the system?
So I added a pole and a 0 to the system in my compensator, and I can shape my root locus. After you get a little bit of intuition on this, you will understand how much I need to move something around. All right. And we'll get to all of that. And it says, okay, I know I can't reach my specs just by, I did my root locus. I figured out I couldn't reach it naturally, but I understand how adding different things is going to change my root locus. And therefore I say, okay, I need active compensation. I need compensation that is more than just proportional feedback. All right? I'm going to need feedback plus, in this case, a lead. All right? A lead network. And I'm going to put this in, and it's going to bend my branches, not much, by the way, but enough to get into my area of acceptable specifications. All right? And I say, aha, now, pick those 2 points and I'm done. All right? So this one is coming in here. So this one's going to end somewhere in this place, okay, for the closed loop pole, and it's going to have a slow response. But because there's a 0 right next to it, right, it's going to have its effect is going to be quite attenuated. All right? So therefore, the 0, being in the proximity of the 0, has the effect of essentially, because if they were right on top of each other, the pole and the 0 would cancel, and you wouldn't see anything, all right, of the response. So it has the effect of attenuating that response. So it'll be there. There'll be a slow e to the minus at mode in the system, and you won't be able to get rid of that. Right? The only way to get rid of that would be effectively to come in and you say, all right, I'm going to drop a pole right on top of that 0 and cancel it, and put another 0 out here, which is a lag network, and say, okay, and just suck it straight across and over there, and I'm not going to see much of that. All right? Generally, pole 0 cancellations are a bad idea. All right? Because what happens if you get it slightly wrong? Right? If you're not perfectly on top of it, you're still going to get the response, but you've made it so you can't control it.
That's why you put it off a little bit.
Usually.
It's like a startup lag, but
once it's going, it's exactly. So there's a couple of different things. Okay. Now, let's take a look at a slightly more complicated system. I have my reference input. I have my feedback. I go through my compensator that we're going to call K0, K of S. So I've extracted the gain from the dynamics of it. Right? Anything that has an S in it is dynamics. It's governed by a differential equation. Right? So it has dynamics in it. I go into my plant, G of S. I have my output Y. I go through my sensor h of s, and I come back in. Okay. Now, the closed loop of this system is going to be 1 plus k naught k of s, g of s, h of s. All right. So if I put it into the k naught k of s, g of s, h of s equals to minus 1, all right. So this now becomes what before I called g of s. All right. In other words, I take all the dynamics of all the different pieces and shove them together, and I'm still looking to see how does that root change, how do the roots of the entire closed loop system change with this gain k0. All right. And so I'm going to go from 0 to infinity and see what happens. All right. And I'm going to wind up with this k naught, some complicated numerator of s, and some complicated denominator of s. Now, these are going to be the zeros, and these are going to be the poles. Now, these are the zeros and the poles of what? Right? I've taken this and I've rewritten it as k naught n of s over d of s. What's in the numerator are the zeros. What's in the denominator are the poles. All right. No, they're not. These are the zeros and the poles of the open loop system. Right? This is break this. Right? This is just going forward out to this point. Right? It's important to remember that what you're looking at are the roots and the poles and the zeros of the open loop system. Okay, that's where you start. Is the open loop system. Right? What you get out of the root locus are the location of the poles of the closed loop system. Right? So, kind of a little tricky here, and I want to make sure you guys sort of get this. All right. So, if I write this in the form k naught n of s over d of s equals minus 1, okay, this has a name. This is Evans' form. All right, as I said, that comes from Evans' root locus, and basically I'm going to look at the angle of this. I want to be 180, and k naught is the magnitude is equal to 1. Right? So I find k naught, that's the magnitude of the whole thing, is 1 to get me what k naught is, and anywhere where the phase of this thing is 180 or minus 180 is on the root locus. Okay. So there are a whole bunch of, so by the way, when this would be kind of the late Cretaceous period when using the spiral. So we can do a little bit better than that. Now you can fire up MATLAB and do this with a single command. All right. So in MATLAB, RLocus. Now, be careful. All right, because you got to learn to do this by hand. All right. To learn to do it by hand, and then you gain the intuition. Once you have the intuition, as I said, you sketch it out. There's a couple of rules which we'll go over, and we'll probably finish about half of them today. And those rules are going to give you what you need to do in order to generate, right, the root locus very quickly to a fairly high degree of accuracy. And then once you're there, you're like, okay, if I actually want to see, do I graze by this thing or do I actually go in, do I actually clear it? Go ahead and fire up MATLAB. You know what to expect. If when you fire up MATLAB you get something very different than what you expected to see, then at this point in time you might say, okay, something is wrong, and I'm not sure what it is, but I need to look at this a lot more closely. All right, it's very important to be a savvy observer. You've got to know what you're expecting to see so that when you see something different, it allows you say, okay, that might not be wrong, but somewhere in the last 20 steps that I did, there's a mistake. Because I should be seeing roughly the same thing with just a higher level of fidelity than I see right now. Okay. So let's start with a couple of these shortcuts. Let's see, where do I want to go? Okay. So there's a whole bunch of rules for the Evans root locus. Let's start with the first one. Okay. So the root locus starts at the open loop poles and ends at the open loop zeros. Okay, so that is, we start at the X's and we go to the O's. All right. Now, let's prove why that is. All right. So I have delta S, right, is equal to 1 plus K naught N of S over D of S is equal to 0. Right? This is my characteristic polynomial, and the roots of my characteristic polynomial are what give me a closed loop response. So I'm looking for where this is 0. We put this in Evans form by saying, well, K naught N of S over D of S is equal to minus 1. All right. But what I'm just going to do is just multiply up by D of S, and I've got that D of S plus K naught N of S is equal to 0. Okay? Which means that when K naught equals 0, I've got that D of S equals to 0, and those are the open loop poles. Right? D of S equals to 0 is nothing more than the open loop poles. Okay? When K naught is infinity, all right, then divide through by K naught, that one goes to 0. I've got that N of S equals to 0, which are nothing more than the open loop zeros. Now, what about the zeros that you don't see? So this all works fine if I say, hey, I've got a pole here, a 0 here, a 0 here. Okay. Then the root locus of this is going to be that these two shoot towards each other, they break off, and do that and wind up, the two poles, the branches end at the zeros. No problem. However, what if instead I have my pole here, and a 0 here? Right? So they're going to start at the open loop poles. Okay? They're going to go to the open loop zeros. One of these is going to that one, and it's that one that's going to go there. The other one is going to head off to the remaining 0 that's at minus infinity. Okay? There are going to be some zeros out at infinity that whenever there's a mismatch, there's going to be zeros at infinity, and we'll figure out where to place them so that you actually hit that. All right.
Why are the zeros at infinity? Because the zeros and x's have the same number? Or?
Right. So so the thing is you're supposed to you're going to end up here, and all the branches have to go somewhere. So the ones that go to the ones you can see go to the ones you can see. The other ones go off to infinity where the other zeros are. All right, that you don't see. All right. So those are the ones. Okay. So that's the first rule. So the first rule is that it starts at the open loop poles, goes to the open loop zeros. Okay, relatively straightforward. All right. The next rule is So what you say is there's going to be like a little recipe of how you do it. All right, you go through and you do all of this, and it comes through, and basically they teach you sort of rules of how to sketch this, and then you start sketching a whole bunch of them. Okay. So this one is that points to the left of an odd number of poles and zeros are on the locus. Okay? And we'll be able to see this one pretty easily. So let's do an X, O, X, X, O, O together, another X. Okay. So if I take my probe point and I start here, all right, then the angle from all of these, all of them, are 0. Right? The angle to this one is 0, that one's 0, that one's 0, that one's 0, those two are 0, that one's 0. Right? So the angle here is 0. Right? Now, as I move my probe point inwards, when I'm here, I've got the angle here is 180. All the rest of them are 0. Right? So I'm at 180. Okay? In this case, minus 180 because it's a pole. Okay? Now, when I pass this point, okay, I've now got 180 minus 180 from this one, plus 180 from that one. Right? Plus because it's a 0, not a pole. So minus 180 plus 180, I'm back at 0 again. All of these guys still giving me 0. Right? As I pass the next one, right, now I've got 180, minus 180, minus 180, plus 180, back to minus 180. Right? Zeros from these guys out. I can keep going through, and basically, every time I pass one, I pick up another 180 degrees. When I have an even number, so I'm looking for an odd number, right? So as long as I'm to the left of an odd number, then the real axis is part of the root locus. When I'm to the left of an even number, then it's not. Right? So in this case, right, looking at this one, let me get rid of those two. Damn. So in this case, the root locus is going to be in between these two, not in between, not 2. So still no, and then that one out to infinity. Right? What happens if I have a complex conjugate pair? Yeah, Andrew.
Is this similar to like branch cuts and analysis?
No. This is just, we're strictly evaluating phase of complex numbers. I mean, it's sort of a philosophical point. You know, all we're doing is we're looking at the phase of a complex number, right? And that complex number is a ratio of complex polynomials, which we don't really care. As soon as we can factor them, we can essentially evaluate the phase graphically, all right? And by evaluating it graphically, we can get huge amounts of information out of the system without. I mean, not only can I now tell you, can you now take a fairly complicated, constant coefficient ordinary linear differential equation in about 2 minutes flat, write it down into a transfer function, throw that transfer function up on this, and now tell me how it's going to behave in feedback as I'm actually changing how it's factoring. This is pretty big stuff, all right? And we're doing it with relatively simple tools. All right, and this is why they've lasted as long as they have. All right, if you had to use a computer to do it, it would have died out. All right, the fact you can do it on the back of an envelope with, there's like 6 rules for this in the book. The first 4 are useful, and the remaining ones are kind of useless. So the first 4 are the only ones I'll ever. I may actually show you some of the other ones, but not really sure. But okay, so what happens if I have a complex conjugate pair that I'm going to pass? Right. Does everyone see why? Let's look here again. So I'm going to put two poles. All right. So I'm going to put a pole here, a 0 here. Let me make that a little farther off, and a pole here. Okay? So, again, out here, this one, right, has this angle, and this one has that angle. And notice that they are, one is minus phi, the other is plus phi. That's going to be true for any point along the real axis. So these two never contribute any phase to anything along the real axis. They always cancel each other out. And because all real systems always come in complex conjugate pairs, you never have the case where you have that sitting out there in the breeze. Right? If it's there, it's also here. Right? And the angle between them always the same. All right? So as I'm passing by, right, it doesn't matter. This one's going to, as I pass by this point, right, I'm going to get minus 90 from that, plus 90 from this. All right? Well, actually, in flipped, right, because this is going to be, this angle is minus 90, but it's a pole, so that's actually plus 90. This one's plus 90, but it's a pole, so it's minus 90, plus 90, minus 90, done. Add them together, I'm still adds up to 0. All right? So this is true for all complex conjugate pairs, always. So all I'm looking for is the number on the real axis. So I look at this and I say, okay, to the left of 1 is odd. Oops, that's just my probe point. 2 is even. 3 is odd. Okay? So I can draw the real axis root locus, pretty much instantaneously. Okay. I will put down what number 3 is, and we will get to it again on Thursday. And so here's rule number 3, is the number of asymptotes is n minus m, where this is the number of poles, and this is the number of zeros. All right, so that's the number of asymptotes. The center of the asymptotes is the sum of the poles minus the sum of the zeros divided by n minus m. All right, the way I like to look at this, and the last piece you need to know, is the angle that the asymptotes have is 180 degrees plus 360 times L minus 1 divided by n minus m, where L goes from 1 to the number of asymptotes. All right. These are also in the book. But what this says is how many ever number of poles in excess of zeros that you have, these are the ones going off to infinity. All right. So if I have 3 poles, 1 0, 2 of these are going off to infinity. All right. Because 1 pole is going to wind up at that 0. In this case, because I now know how to do the real axis, I can tell you that that pole is going there. I can tell you that these 2 are going to hit each other and they're going to split, and they're going to go up. Now, the way I like to look at these, if you look at the sum of the poles minus the sum of the zeros divided by the number, all right? So think about having little masses pulling down, okay, and a little bubble floating upwards with the same mass. All right? What you're looking for is, where are these balancing? All right? This is exactly what that is. All right? This is essentially the fulcrum point at which the weights and the bubble balance. All right? So in this case, all right, let's say this is minus 1, minus 2, minus 3, minus 4. All right, so what do I have? I've got the sum of the poles is minus 1 plus so I've got 1 plus 2 3 plus 4 plus 5, so I've got minus 8, all right, minus 2, right? That's why the bubbles float, all right? That gives you a negative sign right there, all right? So that's minus 6, and divide over 2. So it's minus 6 divided by 2 is minus 3, all right? So what that says is there's an asymptote right there, okay? And the angle of the asymptote, I've got two of them, all right, is 180 plus 360 divided by 2, right? So I've got 180, so when L is 1, that's 0. So 180 divided by 2 is 90. And the next one, when L is 1, I've got, when L is 2, right, I've got minus 90. Right? So I've got 1 and 2. One goes up, the other goes down. And so the branches are going to come along and asymptotically hit this asymptote and go to infinity along that asymptote. And we'll get to proving why they're there and everything else on Thursday. One announcement, I'm not having office hours tomorrow because I'm going to be in San Diego. So if you've got any questions, email them to me or anything else. Yeah.
Back question.
Yeah.